And Hamiltonian in magnetic field, you know, it is scalar product. In general, it is scalar product of magnetic field with spin. We write it in this way, and here dimension of H is energy and sigma is Pauli matrices. So Pauli matrices is without the dimension is absent. It is not dimension matrix, and here H has a dimension of energy because H must have, of course, dimension of energy. So we, in order to consider more simplified case, we consider a magnetic field directed along z-axis. So magnetic field is directed along z-axis. So magnetic field H along z-axis. So then let us write Hamiltonian in such a form. It is magnetic field I write as some H omega divided by 2 multiplied by sigma z. So it is just magnetic field which we represent in such form. Of course, H multiplied by omega frequency, it is energy. So H omega, it is dimension, has a dimension of energy, and in our notation, it is just represent magnetic field. So H, or this one, it is written in such form. So interaction with magnetic field directed along z-axis is written here. It is Hamiltonian of spin in magnetic field. We can easily consider evolution of this spin in magnetic field. And now let us consider ensemble of spins, many spins in magnetic field, set of magnetic field of spins. Я мушу зробити зараз знову перерву тут з цими телефонами. Вибачте, секунду. So we can continue. Ви чуєте мене, так?
Так.
So now let us consider a set of spins in magnetic field. So suppose we have first spin in magnetic field, we have second spin in magnetic field, and so on. And each spin interacts with the same magnetic field. Suppose it is value of magnetic field H I write, which is H omega divided by 2. So this magnetic field interacts also with the same magnetic field, H omega divided by 2, and so on. Each spin interacts with the same magnetic field. And now when we have pure state of spins or ensemble of spins in the same magnetic field. So Hamiltonian for each spin is the same. So when we have magnetic field described by, sorry, not magnetic field, but spin described by matrix sigma I it is number of magnetic field. For instance, it is sigma 1 is here, sigma 2 is here, sigma 3 is here, and so on. Sigma I describe spin corresponding spin. Spin first, spin second, so on. So then Hamiltonian for each spin, Hamiltonian H, it is the same magnetic field, sigma IZ. Magnetic field is the same for each magnetic field. So then we have pure state, and let us consider evolution of this pure state. We can easily calculate evolution of pure state, and let us do this. So evolution of pure state. Maybe we can continue here. So let us, at the time t equal to 0, we have state psi 0, which is superposition of two states, arrow up and arrow down. So A arrow up plus B arrow down. It is, in fact, general state of spin, two-dimensional Hilbert space we have here. And in the initial state, we have a given this amplitude is A and B. It is fixed complex number here. Then let us consider evolution of this state. Evolution, in order to get evolution, we must to apply evolution operator to this state. So psi in time t is, sorry, once more. Oh, sorry. So we consider evolution of this state in time t. We must apply evolution operator. It is Hamiltonian. It is evolution operator, unitary operator, which acts on state psi 0. So it's very simple, in fact. Let us put here Hamiltonian H. So we obtain the following result. It will be A minus H. H is cancelled. I omega divided by 2 times t, which acts on state psi 0. Let me write also in form which we have here instead of psi 0 concrete form, state up arrow, B arrow down. So we can calculate in very simple, sorry, I forget here to write sigma z. So sigma z. I verify it's the same notation or some another notation. Okay, it is the same notation. In the same notation. Okay. So as a result, we obtain the following state. Let me write psi t here, state. It will be equal. Because arrow up, arrow down is eigenstatus of this operator, that component of Pauli matrix, we can easily calculate the result, and let me write result. It will be minus I omega divided by 2 times t. For arrow up, we have here plus, multiplied by this initial amplitude of state, arrow up and plus, and here we obtain minus minus, we obtain plus omega divided by 2 times t, b arrow down state. So we have very simple evolution of quantum state. And now let us consider density matrix. Of course, the same quantum state can be described by a quantum state vector, or we can describe the same pure state using density matrix. So density matrix which corresponds to this pure state, it is psi t, this operator. Let us put this status here and here. So ket vector, first of all, we must write here ket vector. It is this one, ket vector, divided by 2 times t, a arrow up plus exponent b arrow down, and multiply it by bra vector. It is a conjugated vector, so we obtain exponent. Here we will have plus I omega divided by 2 times t arrow a arrow up plus exponent minus t arrow down. So let us continue. So sorry, I forgot, it is mistake here. Here it must be written in opposite direction, this bracket, because here we have bra vector. So first term we obtain, and here conjugated, A conjugated, B conjugated. So first term exponent is cancelled. A squared absolute value, squared absolute value, arrow up, then plus. Then we multiply first term and second term, so we obtain exponent minus omega I omega t, arrow up, arrow down, plus. Then we have a product of second term on the first term, so it will be exponent with plus t, arrow down, arrow up, and finally first term and second term and second term. So we have exponent is cancelled, b absolute value is squared, arrow down, arrow down. So density matrix can be written in such form. Let us write this matrix. In fact, it is operator. This operator in matrix form. It is not problem to write it in matrix form. In matrix form, this operator, let me use the same notation. It will be equal.
Перепрошую, там А і Б нема добутків.
I forget here. Yes, thank you very much. So here we have product. This term is first term and second one. It is A multiplied by B conjugated, and here we have A conjugated multiplied B. It corresponds to arrow down, arrow up. It is B, A conjugated. Okay, A conjugated B. All is okay now? Okay, so let us write in matrix form this operator. It's simple task to write this matrix. So diagonal element A squared, B squared, absolute value squared, and here we have A, B conjugated, exponent minus I omega t, and here A conjugated B, exponent omega t. So we have such matrix, which in fact represent pure state written here. So the same pure state can be described by vector, this vector, or it can be described by density matrix, this one. It is absolutely the same quantum state. And you see that we have two different forms for describing the same quantum state. It is pure quantum state, the same pure quantum state. So, sorry, знову невеличка перерва. So here I write density matrix for which corresponds to pure quantum state. Evolution is, in fact, this density matrix describe evolution in time of pure state. Each spin is interacting with the same magnetic field. And so in time, as we see, each spin is described by the same quantum state. Time is changed, but first spin is described by this vector, second spin is described by this vector, and so on. It absolutely is the same as this matrix. So time also is here, omega is the same for each quantum spin. So we have, in each time, we have once more pure state, because all spins are in the same quantum state. So when in the initial time we prepare pure quantum state, as a result of evolution we have the same quantum state, not the same as in the initial state, but each spin is in the time is described by the same quantum state. All parameters is the same for each quantum, each spins. So in time we have evolution which does not broke coherence of quantum state. When in the initial state we have psi 0, second spin is once more psi 0, and so on. As a result of evolution, we have that first spin described by state psi t, second once more the same state psi t. Psi t is written here. It is the same state. Each spin is described by the same state. So in time we have once more pure state. It is pure state, is the initial state. And here we have once more pure state. So we have coherent state. In each time we have coherent state. And now we consider more interesting situation, and the situation which is related with experiment. Suppose that you want to consider really in the nature such system. What problem appear? In fact, when you want to realize pure ensemble of pure status, it is not simple task for experimentalists to satisfy the same magnetic field for each spin. Of course, as a result of different problems which appear, each spin can interact with different magnetic field. So we can have fluctuation of magnetic field, and situation in the real experiment looks as follows. First spin can interact with magnetic field, so first spin interact with magnetic field H1, second spin interact with magnetic field H2, and so on. So spin I interacts with magnetic field HI, and so on. So each spin is described by some another Hamiltonian. Hamiltonian for first spin, H1, let me write here. It will be H omega. Omega 1 corresponds to just to this magnetic field, sigma Z1. Here I write that it is 1 corresponds to first spin. Second spin interacts with another magnetic field, so Hamiltonian is some another. It is omega 2 sigma 2 Z, and so on. And H I spin with number I interact with another magnetic field, omega I sigma I Z component. So we have all interaction only with magnetic field directed along Z-axis, but value of magnetic field is for each spin is different. We have different magnetic field for each spin, but directed only along z-axis. Maybe you have a question concerning problem which we will try to study now, starting from this definition. Чи маєте, може, питання до цієї постановки задачі, яку ми зараз плануємо розв'язати? Чуєте мене?
Так,
Чуємо. Нема.
Ну і зрозуміла задача, яку ми хочемо розглядати. Значить, до цього часу ми мали набір спінів, які знаходилися в тому самому магнітному полі. А тепер ми маємо набір спінів. Ну, кожен спін має своє місце, і в цьому місці, де знаходиться спін, магнітне поле може бути трошки інше, з різних причин. Магнітне поле Землі впливає. Не можете забезпечити абсолютно те саме магнітне поле. Є флуктуації магнітного поля від спіна до спіна. Магнітне поле міняється. So now we have a task, we have a problem to find evolution of this system in time. And let's in the initial time, we have pure state. We can prepare each spin in the same quantum state at the initial time. So we have the same situation as we have here. At the time t equal to 0, we have the same initial state as here when each spin interacts with the same magnetic field. But at the same time, at the time t equal to 0, we have situations the following. Each spin is in the state psi 0, first spin is psi 0, once more psi 0, and so on. Psi 0, which is equal to A arrow up plus B arrow down. But interaction is with different magnetic field, and so as a result of evolution, here we obtain, let me write psi I, which corresponds, sorry, let me write psi 1. Psi 1 is the same, let me write in such form, psi 1 is the initial time, is this one, psi 2 in the initial time is the same, and so on. Psi I in the initial time is once more the same. So in the initial time we have pure state. And now let us consider the evolution of this set of spins. Magnetic field is different for each spins. So as a result, psi 1 in time t have the following form. We have absolutely similar result as for pure state, where we obtain the result is written here. Look here, but only omega will be corresponding to first magnetic field. So it will be I exponent minus I omega 1 divided by 2 times t. A initial amplitude is the same, arrow up, plus exponent omega 1 divided by 2t, b arrow down. So for spin I with number I, evolution psi I in time t, it will be exponent minus omega I. It is imaginary unit I, but here it is number of spin I. It is the same notation, but I think you understand this. T imaginary unit omega I divided by 2 times t b arrow down. So we can see here that at the time t, state of each spin is different. At the initial time, we have the same quantum state for each spins, but as a result of evolution is in different magnetic fields for each spins. We have that state at time t for fast spin is this one, for second some another, for state psi I we have some another quantum state, because parameter omega here and here is different. We can also describe this situation with the help of density matrix. So density matrix with the, in fact here we have mixed state, mixed quantum state. That is mixed quantum state described by this set of spins can be described by a density matrix, and in this case density matrix will be the following. It's not problem to write. Let me write for the density matrix which corresponds to spin psi I. So it is density matrix which related with evolution only one spin. So this density matrix is the following. It is A squared, AB squared, but only this is magnetic field another. We have another magnetic field. For I and I here, we have another magnetic field. And B squared. So density matrix of this mixed state rho, it will be probability to find state, to find magnetic field with value. So let me use for probability some another notation, the same as here. P I and rho I. So Pi, it is probability to find that spin interacts with magnetic field omega I. So Pi, it is probability P which depends on the value of magnetic field. So density matrix which describe this mixed state is this one. It is a mixing of pure state, rho I, it describes pure state, this one. But here we have a mixing of this pure state. The situation which we, very similar to the, which we use when we considered mixing of pure state, and when we obtain it density matrix corresponding to mixed state. So we can continue and suppose that we have a continuous distribution of magnetic field P, which depend on continuous variable omega. So P, probability to find is this situation magnetic field with value omega is this one. So for density matrix we obtain that it will be, instead of this sum, we obtain integral over omega, pi as function of omega, and rho with which corresponds, I corresponds to magnetic field omega. So when we use this result, we can continue and write density matrix rho. So as function of t, it will be integral over omega distribution function of magnetic field, and here density matrix A squared So we can continue and write result in the following form. It will be a squared. This first element of matrix does not depend on magnetic field, this one and this one. And as a result of integration over omega, we obtain 1, because integral with distribution function, it is 1. It is law of conservation of probability. So total probability is equal to 1. So therefore here we have 1, and here we have mean value of this exponent with such distribution. Let me use such notation. Here I just write this notation. It is mean value with respect to omega. Let me write here omega. And next term is here b, mean value of exponent, mean value with respect to omega. Sorry, yes, okay, also okay. And here we have b squared. So we have such matrix. And by the definition, this mean value, it is integral over omega, distribution function, and exponent. So as we see, it is just Fourier transformation of distribution function. From a mathematical point of view, it is Fourier transformation of distribution function p omega. So it is just our result for evolution of density matrix, and this density matrix describe mixed state. Note that at the initial time, this density matrix rho 0 is this one, and this density matrix corresponds to pure state. For the first time, we considered just pure state. At the initial time, we create pure state. So density matrix corresponding to which corresponds to time 0 is density matrix of pure state. You can verify when you put here t equal to 0, you obtain here 1, and mean value of 1, it is 1. So it just exactly corresponds to initial quantum state as it must be. So, but the result of evolution, we obtain density matrix rho as function of t. And now let us consider some special distribution function. For instance, let us consider a Gaussian distribution function p as function of omega. It will be 1 over square root normalization constant. And here, in such a form, we can write this distribution function. So let's look as follows. This distribution function, its maximal value at omega equal to 0, and this function tends to 0 when time, when magnetic field omega corresponds to magnetic field, but omega tend to plus or minus infinity. It is Gaussian distribution function. So this distribution function describes the following situation. We have that magnetic field has with the same probability positive value and with the same probability negative value. So mean value of magnetic field, of course, for such situation, omega, let me write here. Omega, mean value of omega, it is integral over omega omega and function of distribution. If it is equal, for symmetric distribution function, it is equal to 0. Of course, for Gaussian distribution function, it will be 0 because it is symmetric distribution function. And here we have omega in power 1, of course it is 0. So we can easily now calculate mean value of this exponent. So mean value of exponent with distribution function, it is the following integral over omega exponent or distribution function, let us write for the first time, square root and here exponent minus I omega t. It is Gaussian integral, which you know how to calculate such integral, or maybe you remember the result. I write the result which we obtain here. Okay, it is enough place to write this result here. So after integration, we obtain exponent minus gamma t squared divided by 2. So you can put this result here to the matrix, this one. So for density matrix, in this case, rho as function of t, we obtain here a squared, ab squared, and here exponent gamma t squared divided by 2, a squared b. Of course, that because of symmetric distribution function, integral with exponent which we have plus will be the same. So here we obtain absolutely the same result, minus gamma t squared divided by 2 b squared. So density matrix as function of time looks as follows. And now let us analyze obtained result. But I would like to stress once more, when we consider time t equal to 0, we obtain density matrix rho 0, which corresponds to pure state. It is pure state. So at the initial time, we have pure state. But now let us look what we have at time t. And let us consider t which tends to infinity. What we obtain? We can see here that this term at this one tends to 0. Because of course this multiplier tends to 0 when t times to infinity, to plus or minus infinity. So therefore, this term tends to 0, and rho as function of t tends to the following matrix. It tends to matrix A squared. It will be 0 here, 0, 0, and B squared. So we obtain density matrix, which looks as follows. And now let us analyze this result. What it means. What we obtain from the point of view of ensemble of spins. This density matrix describes the following situation. This density matrix describes the following situation. Here, with probability A squared in this set of spins, we obtain spin arrow down, arrow up, and probability B squared, we obtain spin arrow down. So situation is the following. In this mixed state described by this matrix, situation is as follows. For instance, first spin can be in state psi arrow up. Second, once more, can be in state arrow up. Next spin may be in state arrow down. Next may be arrow up, and so on. And probability to find spin arrow up is a squared, and probability to find spin in this mixed state arrow down is b squared. So it is state which is absolutely mixed state, and here we have no coherent status. Let us remember just now that at time t equal to 0, each state is in the state arrow up a multiplied plus b arrow down. Second spin once more is at the time t0 is once more at the same time at the same state, and so on. And we have once more b a arrow up plus b arrow down. So at the initial time, each spin is at the same quantum state. We have pure quantum state. This one. But as a result of evolution in time t, we obtain this state. When t tends to infinity, we see that we obtain absolutely mixed state, and we have no coherence. We have arrow up or arrow down, and so on. But here we have superposition of two states. At the initial time, we have superposition, this one and this one. But after evolution, and when time tends to infinity, we have no coherence, and such properties or such process is called decoherence, the coherence of quantum state. It's a very simple example where we obtain just decoherence. Just a moment, a few minutes. So, okay, so we get here very interesting result, namely, as a result of evolution of ensemble of spins in fluctuating magnetic field, we obtain mixed state. At the initial time t equal to 0, we have pure state, but as a result of evolution of this pure state at initial time in fluctuating magnetic field, we obtain mixed state. So pure state is changed as a result of evolution to mixed state, and such process is called decoherence of quantum state. Here we have coherent state. Looks once more. I would like to stress this result once more. Here we have coherent state. First spin is in coherent state. second spin is in coherence, and so on. So density matrix which corresponds to this pure state is written where it is written, not you can find. Okay. And after evolution, we obtain this state. We have no coherence, and this state is described by a mixed state, and such process is called decoherence of quantum state. And here we look that this decoherence is related with this zero. These elements, this one and this one, at t tends to infinity, tend to zero, and this just this leads to the coherence of quantum state. So with this we can finish it today, the coherence of spin in fluctuating magnetic field. So as I can see, time is over. Maybe you have questions, comments. Так, чи ви чуєте? Нема питань? Добре. Нема питань. Наступний раз ми бачимося коли з вами? Коли в нас лекція, я з тими лекціями вже додатковими парами сплутався, мушу глянути.
Вівторок.
У вас вівторок, а є ще у нас додаткові пари в понеділок, так? Лекція лишається зараз. Давайте я дивлюся, що тут є. Значить, лекція є в вівторок, і ще лекція у нас є в п'ятницю. В п'ятницю яке в нас буде число? 18? Так, ще в п'ятницю, ще в нас 2 лекції. Понеділок, вівторок і п'ятницю. В понеділок у нас ще є, що у нас є? 12 година, в нас є фундаментальні проблеми в групі, так? І є в 3 годині, це додаткові лабораторні, вони також будуть. Ну, ви той розклад знаєте, так само, як минулий тиждень у вас було лабораторні роботи. Так само і цей тиждень ще будуть, наступний тиждень додаткові лабораторні роботи і додаткова лекція. Це ми відробляємо ті 2 тижні, які у вас не було на початку семестру. Добре, чи є питання до цього? Добре, тоді все на сьогодні. Все, до побачення, всім успіхів.
До побачення.
До побачення.
Гарного дня всім, до побачення. І поменше